Alright, so let's say given this diagram here of an aircraft traveling in space, and the question says, the engine of a rocket in outer space is turned on. The rocket ejects burned fuel at a constant rate. In the first second of firing, it ejects 1 over 1/20th of its initial mass, MO, at a relative speed of 2,400 meters per second. What is the rocket's initial acceleration? To start, the equation we need to use to solve is derived from the conservation of momentum, given by this equation here, where A is the acceleration of the rocket, VEX is the velocity of the expelled gas, MO is the initial mass of the rocket, and then change in mass over change in time, this is the change in mass over change in time of the rocket. So we can identify the variables in the question, starting with the acceleration. This is what we're trying to solve for. And the velocity of the expelled gas, we can see here in the question, it says the rocket ejects gas at a constant rate, and it gives this value here, 2,400 meters per second. Mass O, the initial mass of the rocket is not given explicitly, so we can assume that we don't need it to solve. Change in mass over change in time, it gives that it ejects 1/120th of its mass in 1 second. So change in mass over change in time, you can remember that at a later time, the mass is 1/120th of its initial mass, and at the later time, it's 1 second. And we know at the initial time, the mass is MO, and the initial time can be assumed to be 0. And so this is going to be our change in mass over change in time. So now we have everything to solve. We can just simply plug it in. So this is our equation here, and we can plug in the values we just found for the velocity of the expelled gas and the change in mass over change in time. And we can notice that the initial mass cancel. That's why it wasn't explicitly given in the question. And then also the negatives cancel. And so we get this expression here, and then we can do simple division and get this for the final answer. And so this is the acceleration of the rocket that resulted from the thrust of the rocket losing 1/120th of its original mass. And note, this answer did not depend on the initial mass. So if the velocity of the expelled gas is the same in the following two cases, the initial acceleration for a 120,000 kilogram rocket that ejects 1,000 kilograms per second of fuel is the same as for a 60 kilogram astronaut with a small rocket ejecting 0.5 kilograms per second of fuel. Why? If we apply this equation here, this is our equation that we've been using, to the first situation where the mass of the rocket is ejecting fuel at a constant speed of 2,400 meters per second, and we plug the values in, we can see that the acceleration is equal to 20 meters per second squared. But then if we use the mass of the astronaut instead, and he's still ejecting fuel at 2,400 meters per second, you see the acceleration is still 20 meters per second squared. So it doesn't rely on the initial mass. And a key concept is that the thrust provided by a rocket equals the exhaust speed multiplied by the mass of the fuel ejected per unit time. And this can be seen by looking at our equation here. If we bring the initial mass to the other side, we know that force is equal to mass times acceleration. So this is going to be equal to the thrust force. So we can plug that in. So this is the relationship between the thrust force and the change in mass over change in time. And we can also see that the results in this expression here. So the resulting acceleration is the thrust force divided by the initial mass.